always mention. It's like, where's the video for the last lecture? Oh, I forgot to push record. But I didn't, because here it is. Okay, so let's go ahead and take a look. So we want to take a look at the properties of water, and this is kind of like the sort of the end of chapter 2. So we kind of talked a little bit about chemistry. We talked a little bit about some of the underlying pieces of chemistry, the foundational principles of chemistry, and now we're basically getting to the place where we have more application of chemistry for our purposes. And so in particular, we want to focus our discussions on water and the properties of water. And a couple of things I want to do, first of all, to start off is to kind of show you a little bit, because last thing we talked about actually was this right here, right? The kind of the structure of water, the basic structure of water. But what I wanted to do is I wanted to start off today with kind of taking a look at what water looks like a glass of water, right? So what it looks like when you got a lot of water molecules together, because that structure is actually kind of important to sort of lay some of the groundwork for the properties of water that we then will take a look at here in just a second. Now, for the properties of water, the one thing to always remember, and I want to add a slide, so I'm going to add that now, and we'll kind of go back and forth with it, because I like to keep it sort of all in one place. But when you take a look at water, all the properties that we're going to be taking a look at are given to us by the simple structure of water, right? It's a fairly simple molecule, right? 1 oxygen, 2 hydrogens. It's polar, and it has the capacity to form hydrogen bonds. Pretty simple, but it gives us a huge spectrum, just that simplicity, just a huge spectrum of abilities. And so I'm going to keep kind of a running list here, so it's all in one place. Now we'll kind of come back and forth on that one. So what I want to do is first of all start off with, what does water look like, right? So here we have like a little water strider, and one of the things I want to do in this section isn't just to say, oh, isn't this cute, right? Here's the structure of water. We all feel good about it. It's like some sort of a little, whatever, trivia, right? So just kind of like useless information kind of a thing. But what I want to do is I want to basically give you not just the property of water, but then also connect it to why it matters biologically. So why is this an important property for us, and setting the stage for a biological organism to build itself on? So what's its biological application? The first thing actually is to take a look at what this looks like here, not him, not the strider, but the water itself, right? And this is true for water wherever you have it, whether you have it in a glass that you're drinking, or in your bathtub, or just pouring out of the faucet. When you take a look at water, because it's polar, it's going to have your negative oxygen side, right, and your positive hydrogen side. Now, what happens when you have a bunch of water molecules together is they basically start to zipper up to each other. So that little hydrogen is going to see the negative oxygen of an adjacent molecule, and that right there is your hydrogen bond. But it doesn't stop there, because you have other water molecules involved here. And so this guy's going to see a water molecule, and this guy's going to see an adjacent water molecule, and this guy's going to see an adjacent water molecule, and this guy is going to be seen by these guys, who's going to see an adjacent water molecule, who's going to see an adjacent. What, you get the idea, right? So you kind of start to form this kind of network of waters that kind of starts to form this sort of fishnet-like structure. Okay. Now, what that gives us is basically this kind of network. So the water itself is all zippered together with all these hydrogen bonds, all interlinked with each other. Now, there is a certain, the first 3 properties are associated with that particular phenomenon. So we're going to talk, first of all, about cohesion. We're going to talk about adhesion. And then we have surface tension. So let's define these first of all. So cohesion is the attraction of water for itself. Adhesion is similar, but in this case, it's the attraction of water, not for itself, but for a hard surface. And then surface tension is the force required to overcome the cohesion of water and break its surface. So cohesion is the strength of the water molecules zippering up to each other with these hydrogen bonds, these electrostatic interactions. And that is a fairly strong attraction between these water molecules. Remember what we said about the hydrogen bond. A single hydrogen bond is fairly weak, but you can get great strength when you have lots of them, right? Remember the example of the gecko, right? You can walk up glass if you have lots and lots of hydrogen bonds. So any one hydrogen bond between two water molecules is fairly weak. But when you have a lot of them together, like for instance, in a glass of water or in a lake, then that cohesive forces can actually be quite strong. Now, what does that mean for the purpose of surface tension? Well, let's take a look at a biological application. We're going to start with surface tension, and then we're going to go to cohesion, and then we're going to come back to adhesion. So you kind of have to talk about all three of them a little bit at the same time. That's why I wanted to bundle these guys together. So let's go back to our water strider, right? So the question is, what allows this water strider to be able to skitter around on the surface of the water? Well, it's the surface tension of the water. So what does that mean? So what that basically means is, remember, the surface tension is the force required to overcome the cohesion forces of water. So that means you have to have a sufficient downward force. So this guy does not have enough downward force to overcome those cohesive properties of water. Why? Because he doesn't have much mass, right? So your mass, the gravity pulling on your mass is going to create a downward force. And if that doesn't equal or exceed the cohesion of the water molecules wanting to hang on to each other, then you're not going to sink. And for this guy, that means you're going to be skittering along the surface of the water. Now, if we tried this trick, we'd sink like a rock, right? Why? Because we've got more mass in the water strider, which means more downward force, which does overcome the cohesive forces of water, and so we sink. Okay. And so ultimately then your surface tension is intimately bundled into this concept of cohesion. Now, what does this do for us biologically? Now, it's kind of cute, right? I mean, you've got a little guy there skittering across the water, so that's great. So today, he doesn't drown. That's a good thing, right? That means he gets to live and reproduce, so that's a good thing. But if you think about it, there's actually a greater biological application. Think about it for a second. A lot of these properties of water essentially creates the world we know. Okay, and there's a reason why the world we know is good for life, right? But if you take a look at this, underneath the water, you've got an entire ecosystem, right? I mean, you got fish down there, you've got plants, you've got all sorts of little things underneath the water. Above the water, you've also got another ecosystem, right? You've got us, basically, and our air-breathing ecosystem with all sorts of animals and things like that. But what this surface tension thing gives you is yet another ecosystem. Where? Right there at the interface of where water meets air. So you don't just have some lonely little water strider skittering across the lake. You have an entire thriving ecosystem right there at the interface. And because of the surface tension of water, it allows you to be able to have that bustling metropolis. When spring hits and things come back to life, find a nice lake and just watch it. Like, just watch the surface and just watch how much activity is going on right there at the surface. Not underneath, not above, but right there at the surface. there's like on a good lake, there's a lot. I mean, there's a lot going on. There's a lot of things happening at that surface, at that interface. So it's like an entire habitat in its own right. Why? Because of the surface tension of water. So if you're an insect who likes to live in that area, guess what? You've got a chance to live. That's a good thing. So here now already, just with the surface tension of water, it creates a habitable zone so that some organisms can actually live and survive and reproduce. So it supports life. So that's a good thing. Okay. Now, what about adhesion? So adhesion, I'm going to give you a couple of examples. Obviously, we have this one here. We're going to use this one. We'll kind of expand on this, and I'm going to give you two examples or two real life situations of where adhesion is at play. Sometimes you don't even realize actually it's at play because you don't really know what you're looking at because you never thought about it in terms of that adhesion. I'm going to give you a biological example and a non-biological one. First of all, let's explain what it is. So adhesion is best illustrated with what we have here, which is a capillary tube. Anybody ever use a capillary tube? Oh, but you have. All of you have. How many of you have ever used a straw? Gotcha. Right. Yeah. Right. That's a capillary tube. All a capillary tube is, and sometimes like in a clinical setting, there's like certain tests and things like that where you just need a very minimal sample. And a lot of times like a nurse, instead of like giving you the arm job, they'll just like do a little lance of the finger and they'll take out this little tiny glass tube and they'll just kind of like stick it in the blood droplet and it'll kind of wick up and kind of suck up inside the tube. That's capillary action. And then they'll just load that capillary into whatever their analyzer is and it'll tell you all sorts of stuff. Or how about this one? Like a monitor, like either a blood glucose monitor or a cholesterol monitor or an A1C monitor. I mean, there's all sorts of them out there right now. So we have all these sorts of little finger lancing monitors out there. There's a whole bunch of them now. It's not just glucose anymore. But have you ever noticed that some of those monitors have like, they can lance your finger, but then you kind of stick this little thing. It looks like a little channel, like a really narrow little channel. You kind of stick your little blood drop next to that channel, and then so your blood kind of goes in that little channel, and the analyzer reads it. That's actually capillary action. Okay, that's what we're talking about here. That's an adhesive sort of thing. So here's what it looks like. So here you have basically 3 glass tubes of varying diameters, and so you notice that diameter dictates distance. What does that mean? That means the larger diameter your tube is, the lower your rise. So you can see you've got the lowest rise on the big diameter. The smaller your diameter here, the higher your rise. Okay. So your diameter will dictate how far up it goes. Now this is what's happening. Imagine, if you will, and I want to stick this right here. Imagine that we are water molecules, okay? And we are in this beaker of water. We are all interconnected to each other. So I've got access to you guys. So if I like yank on you guys, then I can pull the whole classroom because you'll feel it kind of rippling through the entire group, right? So we're all interconnected that way. So those are cohesive forces, right? That's cohesive forces. We're all interconnected to each other. Now, here's what happens when you get into a glass or a hard surface area. What happens is the water that's rising up through the column will basically touch the glass. And then all of a sudden, for the first time, you'll feel adhesive forces. So it looks something like this if you blow it up. So your water column in here, and you have on the edge, you've got these, this kind of little curl, right? What do we call that? That's the meniscus, right? And so the question is, why does it curve upward on the sides? Well, the reason is because of adhesion, because the molecules that are right here on the side are feeling the glass. They're getting pulled up by the glass itself. And so, of course, we all know that to read a meniscus, you always read it at the bottom of the meniscus, right? Because that's actually where the water level is. The curled up part is just adhesion. It's just you're being pulled up, right? So whenever you will have to read these, by the way, at some point in the semester. So just make sure you read the bottom of the meniscus whenever you read something like that. So here's what's happening in this class. So I've got a hold of you, yes? And we're all interconnected as a column of water. We got that one, that's cohesion. Then what's happened is I feel the glass behind me, and the glass just basically glues me to the wall like this. Well, guess what? I didn't let go of you guys. My hands are still hanging on to you. So in that process, as I get smeared up against the glass, what am I doing to you guys? I'm pulling on you guys, right? And then not only that, but like if I'm hanging on to you with this hand, I'm hanging on to you with this hand. As I get smeared up, I'm kind of pulling you up. So you're getting closer to the glass now. Now all of a sudden you guys are feeling the glass, and you're going to get smeared against the glass, and you're going to pull on everybody that you're attached to. So as we all start to get smeared against the glass, we pull on the column cohesively that we're attached to. And so literally it's like the molecule smears against the glass and then is pulling on the rest of the water column. As you start to kind of creep up the sides and each of those water molecules gets smeared against the glass, each one of them pulls and gives a little tug on the water column, and the water column goes up. So it's literally like you're sort of tethered to the adhesive glass and you're kind of pulling the water column up. So I can pull it up as far as I can go, and then it gets right about here, and I can't really pull it up anymore because I'm now like this direction. The water column's gone past me now. So you guys up there that are smeared with the glass, you're gonna have to pull them, right? So the guys who get smeared up against the glass above me now are the ones pulling them up, and then they get to the point where they can't really push up anymore, right? So the guys above them then start to pull up. So you kind of get this sort of smear, pull, smear, pull, smear, pull, and that basically is what causes capillary action. Now, why does diameter matter? Well, here's it's very simple. Because you're in contact with more glass. Think about it. We are interconnected. We're water molecules all interconnected here. So if we have a large diameter vessel, then if I get smeared against the glass, and there's like a lot of us, let's say there's not just a room full, let's say there's like, hundreds of people, right? We're all interconnected to each other. And let's say I get smeared against the wall, the folks that are immediately close to me will feel that tension, yes? They'll feel that pull, that tug as I get smeared against the wall. But as you radiate outward and get further away from the glass wall, that tug gets less and less and less, to where somebody in the middle of this crowd may not feel any tug at all. So what happens is there's a good chunk of the middle of the crowd that doesn't even feel any adhesive forces because they're not close enough to the wall. Okay. So that's if we have a large diameter. And that's the reason, by the way, why you have a meniscus. So right here in the middle, these water molecules are so far away from the glass wall that they don't really feel that pull, that tug. But as you get closer and closer to the edge, you feel the presence of the wall because you're starting to feel more of a tug. And then when you get over here, you feel a very strong tug, even not just a tug from your friends, right? As they cohesively start to pull you up, but now you start to feel also the tug of the adhesion. Now all of a sudden you're like, okay, I'm close to the wall now. I can feel the wall kind of sucking me in now, okay? That's the reason why you get this kind of graded meniscus. That's if it's large diameter. Well, let's think about this. If it were a small diameter, like if we were all in a phone booth instead, is there anywhere to go where you don't feel the glass wall on the phone booth? No, because it's so tiny, right? So I'm feeling the phone booth, you're feeling it because we're all very close to the glass wall. So we don't have a big area where we can just sort of hang out and not really feel anything, right? So the narrower diameter basically means we feel the adhesion and we feel the cohesion. So it's all basically pulling us upwards, and nobody doesn't, everybody's in contact with it. That's the reason, by the way, in a smaller diameter capillary tube, you get a higher rise because everybody's feeling the adhesion because the wall is just right there next to you, right? It's not like way over there. It's like right there next to you. So you feel that wall and you feel your friends getting smeared against the wall. Okay, literally, you're like in the phone booth as opposed into an open room. Okay. So that's basically what adhesion, how adhesion works. Now, you're probably thinking, well, wait a minute, that's great, but biologically, how does this matter? Well, I'm going to give you two examples of adhesion at play in life. The first one is going to be the non-biological one. I'm going to give you guys a windshield. And we are going to treat one of those with Rain-X, and the other one is going to be without. Anybody know what Rain-X is? It's a brand name, right? Basically, it's a coating, right? You put it on your windshield and it keeps the water from sticking to your windshield. It's a lot more fun to watch, actually. And it's a lot cheaper than having to buy new windshield wipers. By the way, that's like my biggest pet peeve. One of the things I hate the most of anything that I have to buy on a car. I'm okay with tires. I'm okay with brakes. I'm okay with everything else. But those windshield wipers, I'm like, no. I just don't, it doesn't make sense. Oh, your windshield wipers are streaky. Yeah. So, last time I checked, cars were pretty damn big. I can actually see them through a wet windshield. Oh, guess what? They have lights too. So if it's really raining, by the way, if it's raining bad enough to where you can't actually see at your windshield, stop. I mean, honestly, you shouldn't be driving if you can't see. Just pull over. I mean, nothing's going to save you from that kind of a deluge. I mean, that's kind of like God saying, stop driving. It's like an act of God kind of a thing, right? So that's, it cracks me up. I'm like, whatever. And they're expensive too. And they don't last very long. So I'm like, why? Here, I don't need any money. Why don't you just take it and just throw it in a gutter somewhere? I mean, it's like, yeah, no, that's just stupid. So I'll just buy Rain-X. It's easy. Or better yet, I'll save the money. I won't buy any Rain-X. I won't buy any windshield wipers. And I'll just actually watch out for those big, well-lighted cars. Anyway, that's my thing. Yeah. So if you see somebody driving a red 15-year-old Ford Escape with his head hanging out the window during a heavy rainstorm, it's me, right? I'm okay. Getting wet doesn't bother me. That's my problem. But yeah. So let's go ahead and do this, shall we? Let's make it rain. There's our raindrop. Okay, so that's great, right? So that's a typical raindrop shape, yes? Wait a minute, why is it shaped that way? Ooh, nobody ever asked you that one, huh? It's like, wait a minute. Okay, so I never have actually been asked this question before. Well, think about it this way. Have you ever seen an astronaut playing around with water in space? And what does that water look like? Yeah, it's like a perfect sphere, right? The water molecules aren't flying apart. They're just like a perfect little sphere. It's a lot of fun. It looks like Mercury, actually, right? Just kind of like bobbling around there, and they're just kind of playing around with it. It's just like perfect little sphere. Why? Those are the cohesive forces of water that basically are pulling the water in on itself, and it's creating that spherical shape. The water in our atmosphere is doing the same thing. The only difference is, like you said, gravity. Right? The force of gravity is now taking that sphere and pulling on it, and it's distorting its shape, which is the reason why a raindrop has this raindrop shape to it. By the way, if you see it, if it's raining and then all of a sudden, like Matrix style, you see the raindrops all of a sudden become perfectly spherical, that's not a good thing. That basically means we've lost all gravity. The universe is coming apart at the seams, and that's something bad is about to happen. Right. Okay, so let's go ahead and let this raindrop hit the windshield. What happens when the raindrop hits the windshield? Splats, right? And then spreads out, right? And that's why we need our windshield wipers, right? To wipe that off so that we can actually see through that, even though you can see through that. It's a little harder, but you can see. So at this particular point, what's happening? Well, your windshield is made out of what? Glass, right? So this is a situation where your adhesion forces are greater than cohesion. So we've already established the fact that cohesion exists, right? Because you have a raindrop where water molecules are in a nice little package, right? That's the raindrop, that's cohesion. But as soon as it interacts with the windshield, adhesion exceeds the cohesion, and that causes the water to smear out adhesively on the glass surface. Now then, what happens if we rain on our windshield coated with Rain-X? What does it look like? Yeah, right? Little beads, like astronaut style. It's actually a lot of fun to watch because that little beads are just kind of rolling off your windshield and you're just kind of laughing. It's like, ha ha ha. Okay, maybe not that, but because then you'll probably get struck by lightning or something like that, right? That's my luck. But anyway, so right. So what's happening here? Well, in this particular case, cohesion is greater than adhesion. Why? Because cohesively, the water molecules are bound to each other, and when they do that perfectly, they're basically in that little spherical shape. Okay, so Rain-X basically coats that adhesive surface so the water never feels that adhesion. Basically, yeah, it is. I think Rain-X is kind of a hydrophobic kind of a coating. Yeah. And of course, that's a brand name. There's knockoffs of that. So it's just it's like de-icers, right? It's just, there's a million of them out there. But that's basically what Rain-X does. But what you're doing is you're playing this game between adhesion and cohesion. Okay. Now that's all well and good. Now you guys are going to go out and buy Rain-X, right? So I should buy stock in the company when I get to this section, right? It's like have a bottle of Rain-X. Better yet, what I should do is instead of talking about it, I should get a glass sheet and then a treated and a versus untreated and pour hey, do a demonstration for you guys so you guys can see it. That would be cool. Get a little messy in here. But yeah, I'd be like, you know what? This is it's just water. It's just wet carpet. Just dry it off. Anyway, I'll think about that. I'll have to find some glass somewhere and treat it. Because I actually used to do it. By the way, I used to use Rain-X in grad school, when we were running gels, because we had to run really long gels, and I had to pull them off and dry them out. So I had to actually pull it up, but they're super, super thin, so they're almost impossible to handle. And so what I had to do was I had to stick it on a piece of paper and get it off the glass. But in order to get it off the glass, I had to I had to eliminate that adhesion of the glass, because otherwise it would kind of be half on the glass and half on the paper and just tear everywhere. It'd be terrible, right? So I actually used to treat my glass plates with Rain-X. So the gel, we call it the release plate, the one that was supposed to let go was covered with Rain-X, and the one that was sticky was not. So when I pulled the plates apart, it would only stick to one glass plate instead of being half on one, half on the other. Right? That's about a day's worth of work. So if it's stuck to one or the other, you basically just blew up a day and you're starting over again. Yeah, so a lot of misery in grad school, a lot of fun, but yeah, patience is definitely a virtue there. Okay, that's all well and good, but unless you plan on buying some Rain-X anytime soon, how does this really matter? Where's the biological application? That's what we're here for, yes? I'm going Bob Ross on you guys. You guys know you love Bob Ross. Okay, what is this? Yeah, is it any old tree? It's a pine tree, yep. But it's not like the scrawny things here. There's nothing like this. I'm not talking about what we have here in Colorado, these puny little things. I'm talking about the real deal, right? I'm talking about the trees you can drive the car through. What am I talking about? Yeah, the redwoods, right? Those big, gigantic trees. There's some pretty good ones in Sequoia as well, a little further south in the Sierra, which actually had a fire recently. Actually, I want to check in on that, see how those big sequoias fared, because that would be absolutely heartbreaking. because you don't see them like this very often. These things are huge, right? I mean, we're talking about a tree that's hundreds of feet high. Now, that's not like hyperbole. They're literally like hundreds of feet high. They're way up there. So the question is this. This is what I want to ask the question. We all know that plants need water, yes, including trees. So how do they get water way up here? It does rain on them, but no. What? Through the roots. Okay. Let's put the roots in here. I mean, eventually you rain, right? But the rain goes to roots and it has to come. So it's not like, I mean, like, no. Okay, so that's great. So how does the water actually get up to the top? Because when it rains, it saturates the ground, the water's down here. So how does it get up to the top? The way? Yeah, it's the same mechanism as the capillary tube. It's capillary action. Because what's inside the trunk of a pine tree, the vascular tissue, is like little itty bitty tiny straws. They're called tracheids. And they're microscopic. So like microscopic little tubes that forms the vasculature of the pine tree. And so what happens then is by capillary action, remember we said the smaller the diameter, the higher the rise. Well, this diameter here is a visible diameter. We can get a little bit of rise on it. This diameter here is microscopic. So you can imagine how high the rise would be if it's a microscopic diameter. So these little tracheids are basically making use of capillary action, sucking up through the roots into these little tracheids by capillary action, and it's basically getting pulled all the way up to the crown of the tree. So the answer actually is yes, rain, eventually, but there's a lot. So you kind of have the ultimate. So we had to kind of backfill in the rest of it. So you had the end points. And we had to fill in the front points. However, there's another force actually going on here, right? Because at the top of the tree, you've got evapotranspiration, right? So water molecules at the top of the crown of the tree are evaporating. So what does that mean to us? So if we're a group of water molecules in the tree, we're all interconnected, and I'm at the crown, all of a sudden it's like, oh no, it's my turn to leave. Bye, everybody, right? And I'm gone. But now what happens? The column feels a negative space there. And typically speaking, universally, negative space, like negative pressures, things like that, always drive a filling response. That is to say that you always try to go from a filled space to you always try to fill those empty holes, basically. The universe always tries to do that. It's kind of a pressure thing and a fluid thing and a universal thing. You always go from sort of a high pressure, which is you guys, to a low pressure. So you're always going down. We'll talk more about that later on in the semester. But there's always a drive to sort of fill in those negative spaces, that kind of negative pressure area. So when I leave, that negative absence is like screaming universally by physics, fill me. So what do you guys do? You move up and you fill that space. And then let's say Connor's the next one out, right? So then all of a sudden he leaves and then we have to fill his space, right? And then Mobina leaves and we have to fill her space. So what you have is this two motivations. Capillary action pulling the column upward, but then you have this constant filling need as we get evapotranspiration, causing the column to constantly try to fill in this hole at the crown of the tree. That also creates a forward motivation, a forward momentum in the movement of water. And it's sufficient to basically get water all the way up to the crown of the tree. So why is that a good thing? Well, think about it. It's a tree. It's part of a habitat. The redwoods, by the way, which is the biggest, is actually part of a habitat that's very rare, at least up here in the northern latitudes. Technically, the redwood forest is classified as not tropical rainforest, but as a temperate rainforest. It's actually gets enough moisture every year to qualify and actually be categorized as a rainforest. It's the only temperate rainforest that I know of. Because most other rainforests are either subtropical or tropical. That's how much rain. That's the reason why I said I don't want to say no to rain, because it rains a ton up there. But those redwoods right there, that's a temperate rainforest. So if you go to the redwoods, just bring a rain slicker because it's going to rain on you. That's just what it does. So here's our water. So we already see we can form hydrogen bonds between our two waters, but we can also form hydrogen bonds between a water molecule and an organic molecule that's polar, right? So any kind of organic molecule that has this sort of oxygen, hydrogen, or hydrogen, nitrogen sort of a setup where you have this sort of polarity to it, you're going to be able to actually form hydrogen bonds with it. So oxygen or water molecules can do this with either one. Okay, so that's that particular set of properties. Now what I want to do is I want to take a look at three sets of properties that are kind of related because they're somewhat energetic. The first one is specific heat. We'll take a look at that one. The next one is heat of vaporization. And the third one is the solid issue with the solid. Okay, so first of all, what I want to do is I want to define some of these things and then sort of give you some examples of what they are so you can kind of get an idea of how they work. So first of all, the specific heat is defined as the amount of energy needed to raise 1 gram of substance 1 degree C. Which is all well and good, but there, a lot of times that's a very chemistry definition of it. And so a lot of times students are like, okay, but what does that mean? Even if you had chemistry and you went through specific heat, you're still probably like, what does that mean? Right. So basically what that means, and I'm going to give you an example of what that means. Okay. Because what I want to do is that with specific heat is actually a very specific version of a broader concept that you see in chemistry called heat capacity. Heat capacity is, again, defined very similarly. Specific heat is generally more specific to water. So the specific heat of water is essentially the heat capacity of water. So everything else just has heat capacity. They don't have a special name for it. And so basically what this means is that water can absorb energy without changing temperature. That's all specific heat or heat capacity means. Now, here's what I want to do is I want to kind of illustrate this. What we mean by this is I want to do like a little bit of an experiment. I want to go someplace where it gets hot. And not Denver, because it doesn't get hot here. Actually, it doesn't really get hot anywhere in Colorado. Not what I'm talking about. I want to go somewhere where people die. It gets so hot. Worse than that, right? I mean, we're talking like Mojave, Death Valley. They don't call it Death Valley for no reason. I mean, you're talking about places where it gets up to like 150 degrees. That is like bone crushing heat. Okay. Now, I don't want you to go out there and, you know, toil away and sweat and die. I'm not going to kill you today, right? What I want you to do is I want you to take a shovel. You guys are like, okay, great. We're digging graves now? No, you're not digging graves. Just go out there and lay it on the ground. And then go ahead and go into your air-conditioned RV. Just hang out, drink whatever favorite drink you want, watch TV, just enjoy your life, stay comfortable. And leave that shovel out there for a while. And at the apex of the heat of the day, like around 4 o'clock or so, I want you to go out there and I want you to pick that shovel up. What do you grab? Where's the wood? The handle, right? What else could it be made of? Could be plastic, right? Why don't you grab the spade? Yeah, it's flaming hot, right? And in those temperatures, if you grab hot metal like that, you will go to the emergency room. That is enough to actually give you a 2nd degree burn. It happens. So that's the reason why you want to be careful with some of those hot surfaces, because they actually can do damage to you. So now why? Why is the wood so much cooler than the metal? I mean, they were in the same place, weren't they? There was no shade on them. They absorbed the same amount of energy. So why would one be hotter than the other? Heat capacity. Because metal has a different heat capacity than wood. This is the reason why we make the handle out of wood. Because intuitively we didn't realize that, but the reason why we make the handle out of wood is because it doesn't get hot. We don't make the handle of a shovel out of metal, do we? Why? Because we know on a hot summer day when we're working outside, that handle's going to get flaming hot. We're not going to be able to work with it. So intuitively, we actually knew this when we first constructed the idea of a shovel. And we created a shovel with a material that has a very high heat capacity. That is a high ability to absorb radiation, solar radiation, heat, without changing temperature. So as the metal and the wood are sitting there next to each other, absorbing the exact same amount of heat because they're in the same place, in the same atmosphere, for all of that absorption, the wood resists change in temperature. The metal, on the other hand, very low heat capacity. The second it absorbs solar radiation, boom, there goes the temperature. It keeps going, boom, boom, boom. As a matter of fact, that metal probably came up to temperature within an hour. It probably didn't take long, actually, for that metal to get up to temperature because it has a very low heat capacity. That is to say that when it absorbs energy, it changes temperature very quickly. Okay. That, by the way, is an intrinsic property of metals, right? That's part of that whole conductivity of metals. Metals conduct electricity and heat. So the fact that that spade is a metal is part of its physical characteristics. Metals are typically good conductors of both electricity and heat. Why heat? Because they have a low heat capacity. And so they conduct that heat very easily. So you can see that not everything has the same heat capacity. So that's great. But what does that mean for us? Right? What does this mean biologically? Well, let's I'm going to try and do something here. I did it with marginal success. What did I just draw? For you geography fans. What was it? Yeah. My home state. So what's right there? Not in the basin. San Diego's further south. That basin's actually way too big. It should be like half the size, but yeah, it's there. Yesterday, I like totally botched Southern California, but anyway. Think bigger. Yeah, LA, right? What's the temperatures like in LA? Average temperatures. Hmm? 70s, 80s. I mean, probably a little closer to 80s because they're a little further south. But not too bad, right? As we start to move inland, not very far, maybe an hour's we'll drive, perhaps. Hour and a half, perhaps. What are the temperatures getting like? In Southern California, what are you seeing like right in this area right there? Yeah, not too far inland, you get to a city called Palm Springs. Palm Springs, the temperature gets up to more than that. It gets up in the hundreds. It's like the oasis in the middle of the desert. These two big circles, this is basically where you're going to find places like Mojave and Death Valley and the Sonoran Desert, because Arizona is right there. So the deserts kind of cross over the border into Arizona. So this is the same desert system that Arizona is famous for, the Sonoran Desert. We kind of get our piece of it bleeding over into California. That gets us the Mojave and Death Valley. But you can see, how long did it take you to get to Death Valley? Yeah, it's a pretty short drive. Here's another one. How about right here? What city is right there? I left my heart in. That's the Bay Area, right? And I'm so proud of myself because I actually drew like the northern peninsula where Marin is, the southern peninsula where San Francisco proper is, and then the East Bay. So this is like where Oakland and San Pablo Bay right there is right in there. I don't even know what that is. That actually isn't a real thing. I just kind of wiggled it up there. But the Golden Gate Bridge would be like right there connecting the North and the South Peninsula. And so I grew up in this area in grade school. So I was kind of just north of Oakland by San Pablo Bay, which is the reason I'm a Raider fan. That's kind of from those days. But like I'm an East Bay kid, right? And the East Bay and West Bay, we hate each other. So actually, it's kind of funny, right? Being a Raider fan, as the Bronco fans, usually you guys are like, well, okay, so you must really hate the Chiefs. Not as much as the Niners. Actually, as soon as the Niners lost in the playoffs, I'm happy. Pretty much I don't really care what happens. The Chiefs win, whatever. The Eagles win, whatever. Because like I still have like such a deeply ingrained East Bay, West Bay, like animosity thing that it's just for me when the Niners lose, it's like that's like the Super Bowl. It's like there's like we win the Super Bowl, the next one is the Niners lose, and after that it's like a wash. So that's my East Bay West Bay rivalry is stronger than my team affiliations or my divisional affiliations. This is one of the reasons why I'm quite comfortable living in Broncos country, because honestly, you guys aren't Niner fans. So I'm okay with that. But what's the temperatures like in San Francisco? Anybody know? Cool, right? So we're talking probably like 60s, 65, plus or minus 5 degrees or so. But guess what? We're not just talking about 65 in the summer or the spring like it is here. We're talking about 65 all year round. Like all year round. Like most people don't even own a coat in the Bay Area. If they do, that's like some sort of a light rain slicker sort of a thing. That's about it because it'll rain a lot there. But temperature wise, there's no big heavy parkas. There's no snow gear, nothing like that. You can't find any of that in the Bay Area. It's not necessary. It's light windbreaker weather all year round. Now, what happens if I drive an hour and a half inland? What city do I find right there in the middle of California? Not San Diego. San Diego's down here. So this would be San Diego right down there. He's closer to the border. So this one is going to be state capital, Sacramento, of Sacramento Kings fame. For all you basketball fans who are terrible. Horrible. That's why I'm not a big basketball fan, because it's just like the Kings were just terrible, reliably terrible. So at some point you just give up. And that's what I did. So what kind of temperatures do we get in Sacramento? Let me explain a typical year in Sacramento for you. It's a Mediterranean climate, actually, as well as Napa. Napa County, Solano County, the wine country, the famous wine country of California, is right in here between the coast and Sacramento. The reason why it's called the wine country is because it has a Mediterranean climate, which is a similar climate to what is shared in Italy, in the Tuscany area. Now, a typical year in Sacramento starts off with the rainy season, which is in spring, March or so, and the rainy season comes down in buckets, right? So it's not like the Bay Area. The Bay Area is kind of like a slow drizzle, like constantly all the time. It will come down and not stop, right? So like in Colorado, it rains on us really hard. We get flash floods, and then 5 minutes later, it's gone and the sun is out. That doesn't happen in Sacramento. Like when the rainy season comes in, you get the cloud cover in there and it stays with you, raining on you all week long, or perhaps for weeks at a time. So we get enough moisture at that point where entire cities disappear. Levees to our rivers will break, and basically the river will just, entire cities will disappear underwater. And so that's a common thing. But right around Memorial Day, sometimes a little earlier, the rain stops, the atmosphere dries up, and you don't see a cloud in the sky for the rest of the summer. But what it comes out is the sun. And at that point, that's when your temperatures start to move into the hundreds. And it stays there until September. So not only does it not rain in the summer, but everything dies in the summer. So there's not that Midwest green lushness in the summer. That's what I love about the Midwest, right? Because everything's so green and lush out here is just amazing. I was just flabbergasted when I first moved out to the Midwest. I'm like, you mean there's green stuff in the summer? That's amazing. I mean, literally, I got excited in the Midwest because there was actually a rainstorm in June. And I'm like, oh my gosh, it's raining in June. I've never seen this before, because Sacramento, it doesn't rain. You can go like months at a time and not see a single cloud. And that's not over speaking. All you have is just that beat down sun. It's 106 degrees and you have no cloud in the sky. So there's no relief. You can't wait for those clouds to come in to save you. You are cooking like a piece of bacon. And then you have the same thing to look forward to the next day, and 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 the next day. So it stays in the hundreds and stays there. And then in the winter, you get maybe 5 frost days, not snow days. It doesn't snow in Sacramento. If it does, then it's like Armageddon time. You know, it's like end of the world material. 5 frost days, like, and not even the hard ones like we think of, right? The big season killers, the growing season killers, they don't get hard frost there like we do. A frost day in Sacramento is like maybe 30 degrees. That's cold. That's like bone chilling cold in Sacramento. You get 5 of those maybe a year. And then you just wait for your rainy season in spring and it starts all over again. So why, and by the way, in the middle here, you're going to see this huge Central Valley, which is all hot. Everywhere up and down that valley is hot. So if you go further south, you're going to get places like Modesto, Fresno, Bakersfield, hot, hot, hot. Okay. All along the coast, you got coastal mountains and coastal cities. Some of our most beloved cities are there, like LA, for instance. San Diego is on the coast. Santa Barbara is here. You got places further down south below San Francisco, like Santa Cruz and Monterey are up here just a little south of San Francisco. You get San Luis Obispo, Carmel, Pebble Beach for you golfers is all right here on the coast. These are cool coastal mountains, low mountains, but cool and coastal. Foggy, rainy, drizzly, but cool, like 60s all year round. Your temperate rainforest, your redwoods, are up here in the far corner. And then what you have here in terms of a mountain range is the Cascades, which goes all the way up the coast to Oregon and Washington. So if you think of some of the great mountains in Washington, like Rainier and places like that, that's all part of the Cascades. That's the Northern Cascades. In Oregon, like Mount Hood, Crater Lake, that's all part of the Cascade Range. It's a very wet, rainy, lush, green mountain range. Right here, you have the Sierra Nevada. There's Lake Tahoe right there. That's a much drier mountain range and a much more forbidding mountain range. Okay. But notice what we've done here. What we've done is we've carved out a lot of different habitats, haven't we? You've got the Central Valley grasslands, which is more just mechanized farming now. But anyway, it used to be tule fields, right? Grasslands. That's great for you grazers. If you're into more cooler kind of low mountains types of stuff, then the coastal mountains are good for you. If you want to fly across the water and you want to fish like sea shorebirds, like seagulls and things like that, then you got the coast, right? The pelagic coast. If you're a mountain, then you've got the Sierra Nevada. If you need a little more moisture, then you've got the Cascades. If you need it a little hotter, then you can go down here to the deserts. And so you have all these different habitats. Now, what gives us that? Why is it that the temperatures change so drastically just by driving literally an hour and a half inland from San Francisco to Sacramento? What causes that? Yeah, where's the water? Yeah, sitting right out here. You've got a huge heat sink, the Pacific Ocean. That Pacific Ocean is taking in all the sunlight, absorbing it, not changing temperature. And because it's absorbing all that heat and sunlight, the coastal regions are much more temperate. Why? Because the ocean is soaking up all that heat. As you move inland, not very far, you start to lose that shelter from the ocean, and it gets immediately hard. So you're on your own now. When you go inland, it's like, hey, you're on your own because the water's not going to save you now. You're too far away. So you get hotter and hotter and hotter. Now, what does that give us biologically? Rather than just a geography lesson, right? Because we're like, this is great. This is a biology class. I just got a geography lesson in California. Well, no, the reason why California, first of all, let's be honest, not just because I'm a Californian, but if you're studying ecology and habitats, and that's your direction you're going, California is without question the absolute best state on the face of the planet to go to study ecology. Why? Because all of these different habitats have all these different ecologies in there for you to study. It's one of the few places on Earth where you can go to a temperate rainforest and then to a desert in the same geographical location. That is very rare. Think about it. Most places in the world are one or the other. The subtropics, tropics are all rainforest, no desert. The Sahara, all desert, no rainforest. You got the Himalayas, all mountain, right? No grassland. So you have to pick and choose everywhere else in the world. California is the only place where you have so many different habitats all in one place where you can study it. So it's like Disneyland if you're into ecology and environmental science. But why does it give that? Because of our heat sink. It creates these different habitats. And now, as an organism, you may find one of these habitable, right? So it's like, oh, wait a minute, I like it a little on the cool side. So great, go ahead and thrive and live in the coastal mountains. It's like, I like it a little hotter and I need some grass to eat. Oh, go into the Central Valley. A little hotter, a lot of grass to eat there, right? I'm more of a mountain thing. I'm kind of a seed eater. I like pine nuts. Okay, head on up to the Sierra. You can go there. It's like, I kind of prefer kind of a hot space. Okay, then slide down to the deserts, right? So these habitable zones create multiple opportunities for living organisms to live and thrive. Okay, so it gives you options, and that's critical. That's one of the reasons. The reason why we say this is because if we have a diverse ecosystem or a set of diverse ecosystems, then that's naturally going to support diversity in organisms. And what was one of the first conversations we started off with in chapter 1? Diversity, right? That's what we started off with. And these different diverse habitats supports and gives you that diverse organisms. Okay. And that's all part and parcel to the specific heat of water. It wouldn't be the same if the Pacific Ocean weren't there. If that heat sink, that specific heat weren't there. Okay. Heat of vaporization. Heat of vaporization is the heat or the energy needed to turn a liquid to a gas. So what's the heat of vaporization of water? What does water turn into steam? 212 what? Yep, or the alternative, 100 degrees Celsius, right? That's pretty hot, yes? So this kind of sounds like a chemistry thing, yes? Heat of vaporization actually is a chemistry thing. But why is this important to us, to life? Well, let's think about this. What are you mostly made out of? So let's do a little bit of thought experiment. I'm all about thought experiments. Right. Here's what I want you to do. I want you to take some water. I want you to put it on this desk. Not a lot, just a few drops maybe. And then what I want you to do is I want you to take some acetone. Now, where would you find acetone? If I told you to go out somewhere, find some acetone, bring it back, what would you come back with? Nail polish remover, right? And so what I want you to do, same thing. Put a few drops of that right next to the water spot. Don't mix them. And then what I want you to do is go away for a couple of hours. Right? Let's go do lab or something like that. for a couple of hours, and then let's come back in a couple of hours and make an observation. After a few hours, what are you looking at? What does it look like? Just describe what you're looking at. What would it look like? Like literally, what would it look like? You have these two spots, you left them, right? You come back. Now what do you see? The water starting to still be there. What else? So the acetone's gone. Why is it gone? It evaporates, right? How many of you guys have actually tried to clean something off with acetone? It's really frustrating, actually, because like you wet the cloth, you try to rub it off, but as you're it's like disappearing. So all of a sudden it's like, wait a minute, I got a dry cloth again. Darn it. It's like you got to put it on there. It's a little bit of a fight, actually, because it's like your acetone is evaporating so quickly that it's hard to kind of wipe stuff off because it's constantly disappearing on you instead of like, staying there. That's what's referred to as a volatile chemical. So volatility in a chemical basically means it evaporates quickly. Now, what does that mean in terms of heat of vaporization? What that means in terms of heat of vaporization is that the heat of vaporization of water and the acetone is different, right? Why? Because for acetone, the temperature at which it turns from a liquid to a gas is room temperature, right? Which is roughly between 20 and 22 degrees. So it's already turning into a gas at room temperature. Water, what do you need to do to get it to evaporate? Heat it up, right? Now, is it going to evaporate eventually? Of course, right? Is the water evaporating as we have it on the desk? It is, but it's not being driven by heat. It's not a heat of vaporization thing. Usually when water is evaporating, just like at room temperature, it's because of an atmospheric thing. It's because it's responding to the differences in humidity, a very dry air mass, which like going from high to low, you have high water content here, low water content, and the dry air mass, the water naturally wants to sort of fill that back in, and so it evaporates into this arid climate. That's, by the way, what's happening to you. That's the reason why you get so dry in the winter, your skin, because basically the atmosphere is like sucking the water out of your skin, right? Because ultimately what it's trying to do, it's like you see low humidity out here, high humidity in your body, and everything goes from high to low. So you try to basically humidify the air, basically. That's what you guys are, a bunch of humidifiers running around, right? And so that's the reason why you dry out. But here's the thing, and this is what I want you to imagine. You're mostly made of water, yes? Okay, let's change things up. Let's do kind of, what your life looks like. I mean, here you are. You've been around the block a few times. You know what life is like as a little bag of water. But I want to change it. What if instead of made out of water, what if you were made out of acetone? What would you look like right now?
Nothing.
So describe nothing.
Vanished in the air.
So you'd be like a little vapor cloud? If you had the body mass part of it, what would it look like? Like if you kept your cells and all that sort of stuff, and we just took all your water out and replaced it with acetone, what would you look like?
Raisin.
It's a raisin, yeah, kind of like dehydrated, like you're shriveled up, right? You'd be like a piece of beef jerky, basically, right? Because you would have nothing in you. All of your acetone would be in the atmosphere. Can't really do business that way, can you? Can you do chemical business that way? No, right? So evaporating is a bad day, right? That's not a good thing if you're an organism. You don't want to evaporate. That's not a good thing. So what does the heat of vaporization of water gives us? What it gives us is it gives us a broad range to be able to be functional and to have a water-based chemical system, an aqueous system that is able to maintain chemical reactions in it that we need to live. Not only that, the fact that we're made out of water means we can walk outside on a sunny day and not evaporate. We can walk outside on a sunny day in June or July when it's hot and not evaporate. If we were made out of acetone, poof, right? We're gone. That's not good. So what this does is the fact that water has a heat vaporization means that the entire system of your chemical makeup is able to be functional at very robust temperatures. So you have a broad range of survivability. Not only do we have a broad spectrum of places to live, thank you, specific heat, but now we also have a broad range of temperatures to live in, thank you, heat of vaporization. Okay. Now, that's your heat of vaporization. Now, what about this business about the solid being less dense than the liquid? Well, this one right here is crazy talk. This is like chemical heresy. Scientifically, chemically, water should be burned at the stake for this one, right? Or witchcraft, right? Why is this crazy talk? Well, let's take a look at what every other substance on the earth does. What are the three states of matter? Solid, liquid, and a gas. So basically in a gas state, we're going to start there. You've got molecules of whatever substance you are that are spread apart, far apart, right? They're moving around randomly. And so as a result, they tend to be less dense. That is to say, there's fewer atoms per unit space because they're all spread out. It's kind of like if I were to take you guys and spread you out across the campus, right? The density of you guys would be much smaller because there'd be huge amounts of space between each one of you. Okay, that's what a gas is like. As we start to cool this down, what's going to happen is these molecules will start to come together, but they're still kind of moving around, right? So this is kind of like a situation where you kind of start to condense down a little bit, like we're in this room. We're like a liquid. We're much more dense, right, in this particular case, because there's more of us. And so we're kind of like getting in here like a little closer together, right? So as a liquid, we're still pretty good, and we're still kind of hanging out, and that's fine. But what happens then when we continue to cool it, when we go to the solid? In the solid, what's going to happen is these atoms are going to get much closer together. Because we can get more dense. So this is going to be the most dense. More atoms per unit space. So this is kind of like if I were right here between Amelia and Nobina, right now we're kind of like liquid water. We're close, but we're not touching. If we get shoulder to shoulder, that's like a solid, right? Now we're really dense, right? So most solids and most substances are okay with that. So they're really, really tight like that, and they're okay with that. As a result, they're the most dense of the three states, which means if you put solid anything in its liquid, it will sink, right? So that's basically what it does. If you take solid iron and put it in molten iron, liquid iron, it'll sink until it melts. But that's basically what's going to happen. Now, what happens with water? Here's what happens with water. Let's imagine we do the same thing. We're gas, we cool down, now we're liquid, and as we start to get to 4 degrees, which is about refrigerator temperature, then we start to get the most dense. We start as water molecules, we get closer and closer together because that's what we do, right? As we're on our way to a solid. Now, most solids would get all shoulder to shoulder, and we're like, okay, we're really dense now, right? What water does is something different. As soon as you get like to a certain point at about 0 degrees or so, freezing happens relatively between 0 and 4, right? What happens is water says, you know what? We're getting really close, but now too much personal space, right? And so what it does, it kind of pushes each other away, and it kind of creates this little personal space zone. And that actually causes the ice or the solid to expand rather than contract. So the expansion of water is due to this really unique thing water does, which is kind of push away from each other once they get down to that sort of critical point where they're too close. And just like us, right? We get a little too close. We're like personal space, and then we kind of push away from each other, and then that's an expansion. This is one of the reasons why if you put a water bottle in your freezer, what happens to it? It blows up, right? It expands. And so that's what's happening. So it becomes less dense, which means instead of sinking in water, ice will float. Now, what does this do for us? Let's draw a lake. Here's our lake. Let's put it in the middle of winter. Hard winter. what's going to happen to that upper layer of water? So it'll freeze. And then if water were like everything else, where the solid was more dense, what would happen to this layer of ice? It would sink. And then what would happen to the next layer of water? It would freeze, right? So the next layer would freeze, and then it would sink, and then the next layer would freeze, and then sink, and then freeze, and then sink, and then eventually what would happen is you get a frozen lake. Now, if it's completely frozen, you can't support life with that. I mean, yeah, will there be some bacteria in there? Sure. Will there be some archaea in there? Probably. Is there going to be a bustling ecosystem in there? Probably not. Right? So what you've done by freezing solid is you've really greatly reduced diversity. But we know that's not the case, right? We know that ice floats. And underneath the ice, we know there's a bustling ecosystem, multiple ecosystems, right? Because we have entire sections of the world up in the northern latitudes covered by ice that have massively bustling ecosystems underneath the ice shelf. Okay. And that habitable zone of life can only exist if there is liquid water, even if it's cold. But if that ice stays on the top, floats, and doesn't freeze all the way solid, so your swimmers, your fish, your whales can migrate up and down through cold water, things like that. So you can get all sorts of things up there, cold water animals that can live up there and thrive and be prosperous, right? That's the whole point, right? You want to create a situation where life can flourish. And that's what you're doing. Not so much if it's frozen solid, which is actually one of the biggest things I have. And this is actually one of the biggest pushbacks that I have, the kind of raised eyebrows that I have about the theory of snowball Earth, right? Have you ever looked at the origins of Earth? One of the ideas, not the only idea, it's just an idea, is that we think that maybe the Earth went through a phase of like total freeze. We call it snowball Earth. Well, the problem is if you go through an area of total freeze, then how do you actually get living organisms through that, right? Because total freeze is not supportive of life, right? Which is also the reason why we're looking for liquid water on other planets, not solid. Okay. So there are three more that I want to cover. Actually, two more. I'm just going to add two, and I'll cover the other one as a separate one. So the next one is water is a solvent. We're going to take a look at that one. And then, of course, the organizational power of water. And we'll take a look at these two. And I'm done with the list, so I'll leave that, thankfully, for you guys. Right, so let's take a look at water as a solvent. So basically in chemistry, we all learn at some point about this concept of a solution, right, which is typically composed of two pieces. You generally will have a solute in a solution, which is what gets dissolved. And then you'll have the solvent, which is what does the dissolving. That's dissolving. So that just blobbed me out because it's too close to the edge. So what that means is, in the case of biological systems, water is the solvent. Everything that's in water is the solute. Think about it. We looked at a chemical reaction, right, where they had reactants and products. Those reactants in biology are dissolved in water. We call that aqueous. So aqueous reactions are what we are made of. These are water-based reactions. And that's an entire branch of chemistry. And that's actually where you spend most of your time, is in aqueous reaction. So Chem 1, Chem 2, it's aqueous reaction chemistry. That's where you're spending most of your time. If you're in non-aqueous systems, then oftentimes you're in organic chemistry. So that's kind of a different ball game. So this is a completely different shift, like a completely different world, two different, very different realities in chemistry. This is one of the reasons why having liquid water, not just water, liquid water is important, because a solvent has to have the capacity to dissolve its solutes, and gaseous water cannot. Think about it. If you want to prove that to yourself, take steam and try to dissolve salt in it. Is that going to be successful? No, because steam does not have enough cohesion to it in order to be able to dissolve the salt. It has to have that cohesiveness to it, water, liquid water, in order to be able to dissolve the solute. So all those little things that are in us, all the ions that are in us, all the molecules that are in us, all of the reactants that are in us, those are all solutes dissolved in our watery matrix. Okay. Which is one of the reasons why water is so important. So it's a great solvent. We actually have an image of its solvent capacity here. So here's an image of what water looks like as a solvent, as it's acting on salt. So we talked a little bit about the sodium chloride crystal, right? The way that it stacks itself according to charge, right? Positive, negative, negative, positive. What happens is when you put a salt crystal in water, is the water molecules will rip the negative chloride out, and it will surround this negative chloride with its little positive tails, its hydrogen tails, creating this what's called a hydration shell. So it's like a little surrounding shell of water around this molecule. It does the same thing to the sodium ion. So it pulls the sodium ion out, and then in this case, it actually surrounds the sodium ion with its negative oxygen heads, also creating a hydration shell. And in a matter of fact, you can also do this with a polar but non-ionic molecule as well, like sugar, for instance, right? Last time I checked, we can also dissolve sugar in water. Yes, we've all made sugar water before. So sugar is going to be polar. So it's going to have this positive side, this negative side. What's going to happen is water will basically surround the positive ends with its negative oxygens, like this, and it's going to surround the negative ends with its little hydrogen tails, like this. So what you've done is you created a hydration shell. Whenever you create this surrounding hydration shell of water around you, you're basically what's referred to as having been dissolved. So this defines a solute, how a solute gets dissolved in water. So to be dissolved means that you're surrounded by water and that you're incorporated in water. By the way, if you're wondering, that salty taste of sodium chloride is actually the taste that our brain recognizes in its ionic form. So actually the breakup of the sodium and the chloride ion in solution creates the attributes of the taste of the salt itself. So the taste of salt is because of the ionic dissolved ions in solution. So here's a good question I always get asked every now and then when a student hears that. The next question is, well, what does it taste like if it's not dissolved? The answer to that question is we will never know, because our basis of taste requires water. So the second that you try to taste a salt crystal, it's getting dissolved in your saliva. And so you're tasting the dissolved salt crystal. So we don't have the capacity to taste an undissolved salt crystal because we don't have like a dry taste. We don't have a way to taste it dry. My guess is it probably would taste like nothing. Chalk, maybe. I don't know. Nobody would ever know. So that's the water is a good solvent. Now, the other one is its organizational power. And this is important, right? Because in this particular one, we need to define some, we're going to be doing a little bit of anthropomorphizing here, which I always love to do, right? And so we need to sort of describe the nature of the two sides of the molecular world. If you're a molecule in your body, you either belong to one or the other of these camps, okay? The first one is hydrophilic. So hydro means water, philic means love. Phileo is actually the root term, a Greek term for love. It's the root for Philadelphia, as in the city of Philadelphia, which actually means the city of brotherly love. Delphi is brother. So it's love brother. Actually, that's what the term means. So that's why they call Philadelphia the city of brotherly love, is because that's what the name means. So these are water lovers, right? So what does that mean? That means, like water, you are either polar or charged. So all polar and charged molecules fall into this hydrophilic grouping. Now, the alternative would be the hydrophobic. So hydro, of course, means water. Phobic for phobia means fear. These are the water fears. So these guys would be the nonpolar and uncharged molecules. But certainly nonpolar. But I want to drive this into you because it's important to understand, just like we did, like remember with sodium and chloride, we kind of described their sort of chemical temperament with this sort of crazy psychological psychosis sort of a way of looking at things. We want to do the same thing here. And I want to change this a little bit, not from water fears, but I want to change this to water haters. I want a stronger emotion. And not the kind of hate that we are capable of here. So we're talking about. Oftentimes we talk about hate, but we're pretty quixotic, right? I mean, I hate you, which usually means like, I really don't like you. And the next day it's like, okay, I don't hate you as much today, right? So we kind of are all over the place. We're a little crazy that way. No, this one is like, I mean, we're talking about a hatred that like is not capable in like humans are not capable of this. I mean, we're talking about like, you know, a hatred that would be like a supernatural, dark, malevolent hatred, like a seething, frothing at the mouth, bloody foam at the mouth type of seething hatred that is like a consuming fire. It's like just burning you alive, that's the only thing you can think of is this hatred, right? You're just so full of hatred. It's like you literally are out of control. And this is the only thing that drives you. And you're like a fire. You're basically like burning everything around you. Like there's nothing in your life that you love. You're just consumed totally by hate. That's what these molecules are like. So the question is, who do they hate? They hate the hydrophilics. So basically, you can think of a hydrophobic molecule as basically not just being hateful or fearing hydrophilics, but they are so seethingly full of hatred. It's like every second of their existence is totally consumed with the overwhelming objective to try to create a universe that essentially annihilates all hydrophilic molecules from existence. And everything that you do is moving in that direction. That's the reason why I say like this is kind of like a more of like a diabolical supernatural level of hate, right? The kind of things we think of and imagine in theology, sort of the great battle between good and evil, you know, that are just like so big and so it's like it does, and we're just like we're not even capable of that sort of level of stuff. That's kind of what we're talking about here. And there's a reason for that, right? Because that sets up the psychology of the interaction. Now, the question is, would there be some tension between those two? If you had a hydrophilic sitting next to a hydrophobic, would there be a little tension there? Yes, right? I mean, we're talking about like, this is a tension that could split the universe apart. This is how strongly tense this relationship is. Well, now, the great thing about biology is tension is a good thing. Because all tension requires what? Tension requires resolution, right? Think about it. When you're burning, what is the one thing you're striving for? Relief, right? Resolution, a resolution that brings relief. So when the hydrophobics are seething with hatred, the resolution they're looking for, the annihilation of hydrophilics from the universe, is a resolution that they're seeking that brings them relief. So when there's tension, there's resolution. But guess what? From resolution can come function. I'll have a lot more to say about tension resolution because it's a common biological trick that happens actually in biological organisms. So what do I mean then by this whole idea of the organizational power of water, right? Because that's what I listed on our list. So what does that mean? It means this simply. Because of this relationship, and you have to really get this relationship, this animosity between these two, to really get an idea of how powerful this is. Let's imagine all of you guys are non-polar molecules, and I'm water, right? So everybody hates me, and you're just like ripping out of your skin to try to strangle me to death. So if I walk next to one of you guys, what's your natural reaction to that? Run away, right? Because you can't stand being around me. Well, here's a good thing. Let's imagine that what I want to do is I want to take this group here and I want to split you guys in half. I want to reorganize you. Guess what I have to do? Very simple. Yeah. All I have to do is do this right here, right? Just walk right here in the middle. And so here I am right now, right? So what's going to happen to you guys? You're going to like run toward each other and away from me, right? So you're going to probably run to that wall, right? And how about you guys? You're going to run to this wall, probably tear the wall down so you can get further away. Did I have to do anything to do that? Did I successfully achieve my goal? I organized you guys, didn't I? Into two different groups. But guess what? I did nothing for that. I didn't have to create anything. I didn't have to spend a lot of energy to do that. I simply just existed. And I automatically got organization for free. That's big. Whenever you can get something for free in the universe, you got to take it. You got to take it, right? And that is a huge thing. We see the organizational power of water creating structure. So a lot of times when we take a look at biological structure, we say like, well, how did you get this membrane? Well, because of the organizational power of water. You didn't get it because you're like, okay, let's do this and let's add this here. No. All you did was just show up. And it automatically, just because of this animosity between these two molecules, automatically organized itself. Spontaneous. And that's helpful. We'll take a look at some examples of this actually in hardcore biology in future chapters. The next thing I want to do is take a look at the ionization of water. And so this is kind of getting to our acids and bases. And so what I want to do is I want to take a look at, just kind of like our lab 2, right? So we did lab 2 on acids and bases. And so when we take a look at water, we can rewrite water as HOH, right? And what happens with water is it'll dissociate into two things, hydrogen ion plus the hydroxide ion. And we learned that the more of this you have, the more acidity you have and the more characters of an acid you have, right? So what does an acid taste like? Sour. So the more of the hydrogen ion you have, the more sour it is. And also, what does it feel like? So the more hydrogen ion you have, the more burn there is, right? So the increase in hydrogen ion is what determines an acid. And then, of course, this one determines the base. So basically, if you have a greater hydroxide ion, then you basically have greater basic characteristics. So more basic. So when we take a look then at acidity, we have this scale, right, which is a logarithmic scale of pH. And the idea is, you know, where does this come from? So we have a pH scale. I'm going to write it down here. That's a 0 to 14 scale. It's actually, the pH is defined as the negative log of the hydrogen ion concentration. And I mean, I could do an example of that for you guys to show you how that works. But really what I want to do is I want to sort of lay out the scale. So from 0 to like 6.9, this is going to be acidic. What this means is your hydrogen ion concentration is going to be greater than your hydroxide ion concentration. At 7, you're going to be neutral, which means your hydrogen ion concentration is equal to your hydroxide ion concentration. And from 7.1 to 14, you're basic, which means your hydrogen ion concentration is going to be less than your hydroxide ion concentration. Okay, so that's how you define an acid or a base, at least by pH. But here's a big question a lot of times students will have. They'll take a look at this and be like, okay, that all makes sense, right? Because we kind of played around with it, right? You guys did pH paper, you kind of did some of that. So you kind of play around with this a little bit. But a lot of times students will take a look at this and they'll be like, okay, wait a minute. 14? So to do a scale, you pick a 0 to 14 scale. Does that seem a little random? Like if I were to ask you guys, make a scale for pH, most of you guys would probably come up with maybe a 0 to 10 scale or a 0 to 5, right? If you got really creative, be 0 to 15, right? Would anybody have picked 14? It seems really random, right? So a lot of times students will be like, well, wait a minute. So where does 14 come from? Well, it's very simple where 14 comes from. Because when water dissociates like this, when it ionizes, that's what that last property of water is. It ionizes, it falls apart into its ions. We can actually measure the concentration of hydrogen ion and hydroxide ion. As it turns out, the concentration of hydrogen ion tends to be 10 to the minus 7 molar. Hydroxide ion, also 10 to the minus 7 molar in pure water. Now, if you take equilibrium in chemistry, you'll know that basically in order to get the concentration of your reactants, you just multiply the concentrations of your products. So basically what that means is then the concentration of water would be 10 to the minus 14 molar. So the reason why it's a 0 to 14 scale is because of the concentration of water with a midpoint of 7. That's the reason why so it's not random. It's based on and built on water. Okay, so that's one of the important things about the pH scale. So how do we define an acid? So an acid we can define as anything that will basically increase your hydrogen ion concentration. That is to say that you're adding a proton to the mix, because that's what a hydrogen ion is, right? Because how many protons does hydrogen have? 1. What's the mass of hydrogen? So how many neutrons does it have? Right, a proton has 1 proton, has a mass of 1, which means how many neutrons? None, right? So if you take that electron away from hydrogen, what do you have left? A proton, right? Because the hydrogen atom was only made up of 1 proton and 1 electron. So if you take that electron away, what you have essentially is a proton running around. This is the reason why sometimes in some settings, you'll see either hydrogen ion, but that is equivalent to a proton because that's what a hydrogen ion is. It's basically a proton. So sometimes you'll hear hydrogen ion this or a proton gradient, right? So those are the same, those are synonymous, right? So an acid is either going to increase your hydrogen ion concentration or it's going to decrease your pH, right? Either one of those. A base is something that will decrease your hydrogen ion or it'll increase your hydroxide ion if you're a hydroxide bearing one, or it will increase your pH. So the higher numbers of your pH. By the way, you get in chemistry, there's multiple definitions of an acid and base. Which one you use depends on what you're doing. Like in organic chemistry, we use a slightly different definition of acid or base because we're looking at different types of chemistry patterns in there. So this is the most basic one. This is the one that we use in biology. So let's take a look at it, right? We saw this in lab, yes? And so I kind of touched on it a little bit, but I want to dig into it a bit more here. just to kind of show you, first of all, what we're looking at. So for instance, on this scale, we have our hydrogen ion concentration, right? 10 to the 0 is 1. So this is basically a high hydrogen ion concentration. Okay. Remember, a negative exponent means it's tiny, means it's 1 over 10 to the 14, which is 10 times 10 times 10 times 10 times 10 14 times. Okay. So this is a very small or a low hydrogen ion concentration. That's what we're trying to say here. And then, of course, you can see how that's inversely proportional to your pH. So if you've got a ton of hydrogen ion, your pH is going to be very low. And if you got very little hydrogen ion, it's going to be very high. So it's going to be basic. Let's take a look at what we got here, shall we? So coming in at the lower range of your acidity, you've got things like hydrochloric acid, right? This would be like reagent grade hydrochloric acid, something you'd have to get from like a chemical outfit. Okay. So we don't usually have access to this. As we start to move a little higher into the acidity range, we're getting a little less acidic, but still pretty acidic. We're about 2 now. Stomach acid comes in around here. We all know that, right? Because stomach is a very unpleasant thing. So when you're spewing out stomach acid, that's always a bad thing. Lemon juice actually is right around this range for those of you lemon lovers, right? There's a reason why we put like 10 times more sugar in lemonade than actual lemon juice, right? We do the lemon juice and then what do? We dilute it with water and then we dump a bunch of sugar in it, right? That's because of its acidity. It's very acidic. Coming in at 3, we got things like vinegar, like salad vinegar, soft drinks. Most soft drinks are coming around here. Beer, right? Which may be your favorite acid trip. So tomatoes are coming in around 4. This is not surprising, right? Because a lot of people complain about tomatoes because they create sores and things like that. They have a hard time with it because of the acidity of it. Because it's acidic, however, there's a lot of tomato-based dishes out there. And so a culinary strategy, often used culinary strategy, is ways to neutralize acidity in food so that you have less of the acid presentation and more of the flavor. And so there's different culinary techniques that you use to sort of neutralize the acidity and maintain the flavor. Up at about 5, you got black coffee, my personal preferred acid trip. Urine is the first of the non-nasty body fluids that's coming in right around pH of 6, 6.5. That's about normal for urine. And a lot of times this sort of surprises people, right? Because wait a minute, I thought urine was supposed to be like more neutral. It's not. The reason why it's acidic is because we use urine to balance our internal pH, which is right around 7.4. In order to do that, when we get a little too acidic, we dump off that excess acid into our urine stream so that we can keep our internal pH the same. Okay, that's the reason why urine tends to be acidic. Pure water, we just talked about, is 7. Seawater is a little on the alkaline side. It's 8. Baking soda is 9. The Great Salt Lakes, they don't call it the alkali flats for no reason. Coming around at 10. Ammonia is around 11-ish or so. Bleach is coming around 13. Oven cleaners down here as well. Reagent grade sodium hydroxide, nasty stuff. That's about 14. Really bad things. Now, why do I show you this? Is it just a gee whiz thing? No. The reason why I show you this is to show you something very clear, a biological application. Notice what we have up here. We have things that we largely eat and drink. And then down here, we have things that we use to clean up after we eat and drink. Now, you can tolerate acid. Why? Because if I have you guys take a pure lemon and suck on the lemon, am I having to call poison control on you? If I have you guys drink some ammonia, am I having to call poison control on you? Yeah, so you can see physiologically, we have adapted in order to tolerate acids, but not bases. Right, so we have an intolerance for bases. Not only that, but the other thing that's also kind of cool about this, and I just kind of want to drive this point home because it's really cool, is notice that we're talking about the animal kingdom, us, versus the plant kingdom. Tomatoes, beer, vinegar, lemon trees, totally different kingdom. Coffee, totally different kingdom. And yet the two of us, separate from each other, managed to perfectly interweave with each other, almost as if we were working together. Like we knew that we had to interweave with each other. Why? Because if I wanted to eat lemons, I had to develop a physiology that would tolerate lemon juice. If I wanted to drink black coffee or eat tomatoes, I had to develop a physiology from the beginning. Not like now, but from the beginning, when we were all just growing up. We had to create a physiology that tolerated that. So you have two different things happening in completely separate kingdoms, answering our own questions in isolation, and yet at the same time, it turns out we actually had to weave ourselves together, like perfectly. That's kind of an amazing sort of a thing. That's what I mean by biology is this great tapestry, and that all the threads are just intricately woven together, like we all work together. You know, like we kind of planned it all out. It's like amazing how everything just fits together perfectly. This is an example of that. We could have easily chosen this. And if we did, we wouldn't have been able to eat any of this stuff. If we drank lemonade, we'd go to poison control. But that's not the way it worked. The lemon tree is good for food for us. Why? Because we've developed a physiology that allows us to tolerate it. That's like goes way back. That goes like back in the kingdom times. I mean, like between kingdom, Plantae and Animalia. That level of integration is just astounding when you look at how tightly woven it is. Okay. Just a thought to ponder. The coolness of biology moment, right? Okay, so we will pick up with this one on Monday, and then we will finish off chapter 2. Meg.
Is our exam going to be on chapters 1 and 2 or 1 and 2?
It'll be on at least 1 and 2, whatever of free we get to on Monday.